The third trade-off is throughput versus latency. Most of you know what latency is, but I'll just define this. It means the time required to get a response from a server. You send input. The time to get a response for that input is called latency.
Let us also define throughput with the help of an example. Assume you have a server which can run at most 20 instructions per second. Here, throughput will be defined as follows.
How much of the processing power that I have is being spent on tasks which are relevant to the application that I am running. For example, if you have a profile service in Instagram and it spends 10 instructions per second waiting for something to persist to the database, these are all useless instructions. This is the time when I'm not running the application. Another thing could be garbage collection. So let's say 2 instructions are for garbage collection and 10 instructions are for waiting. How many instructions do you have remaining? 8 instructions in a second. Those 8 are spent in the application. So what is your throughput? Your throughput is 8 by 20 into 100, which is 40%. 40% of the time that your application runs, you are running application instructions, and that means this is very poor throughput. Okay, of course, you don't get blocked for so long. Half the time, if your application is blocked on other resources, then there is a problem. In general, yes, this is what throughput means. If you're running 20 out of 20 application instructions, that's like 100% throughput. This is impossible because usually you have some background tasks to be done. And if you're seeing there is no background task being done, that means your application is probably handling many of the background tasks. The garbage collection which is happening automatically in Java, you're doing that yourself. So it's not really an accurate representation, but still, theoretically, you can go to almost 100% throughput. So where is the trade-off? The trade-off comes when you have a set of tasks to do, let us say T1, T2, T3, and some background task. So BG, and then T1 again. How often you run the background task determines what is your throughput and latency going to be like. For example, if you have garbage collection to be done and you say, I am going to take parts of my memory for my application. So first I come over here and pick this part up. Then somebody else comes and picks this part up. So this part is taken away. This part is taken away. Now I come to pick up memory for an object which is this big. It will not fit in this area. It will exceed this area. So I'll, overflow. So I can't do that. Instead of searching nicely, judiciously, or doing some sort of compaction, I say, screw that, come over here, take this whole part. Now I get an even bigger object, which is this big. I can't keep it in memory. I search around memory, I don't find any space. Now I take all the objects and compact them. I compact them into a space like this, right? And then I take my big object and put it here. So what happened here is I kept on adding objects in memory till the point that I couldn't do anymore. And then I did a big cleanup task. I did a big background task. In general, if you are leaving things for the end, background tasks are kept for the end, your throughput is high, meaning you focus on the background task 100% of the time for some seconds, let's say 3 seconds. All your background tasks are finished, and then you again get back to the application for, let's say, 90 seconds or 97 seconds, just to make the calculation simple. Okay, but for 3 seconds, it's like brain surgery is happening. Your application cannot move a muscle. It doesn't have control over the operating system. All the tasks that are happening are background tasks. So any person who comes at this point will be stuck for the next 3 seconds. Any request which comes here. For 3 seconds, you will have a huge pileup of requests, and then boom, at this point, the gates open and everybody wants to access the application, right? So here, throughput is 97%, but worst case latency is more than 3 seconds. Because you have a big flood of tasks here, maybe you might have a thundering herd also coming. You might have a cascading failure. Many problems are also there. But even if you can handle the load, worst case latency is 3 seconds. On the other hand, if you say that I'm going to do small parts of the background task, when first I couldn't find the object, I'm going to do a little bit of compaction. I'm going to do a little bit of compression. Then what will happen is you will be running this background task much more frequently. Maybe some small part of the background task will be run here, BG1, maybe BG2 here, BG3 is here. How is this helpful? It's helpful because the max amount of time that you're stuck doing a background task is much smaller, maybe 0.1 second. But you do this, let's say 90 times. So the total number of seconds which are spent are 9 seconds. So your throughput out of 100 seconds became 91%. You see, this is much worse than 97%. Having said that though, your worst case latency now has gone down to 0.1 second apart from your normal response time. So if your response time earlier was R, then it could be in the worst case R plus 3. Here it is r plus 0.1. So if your normal response time is 0.1 second, worst case it will be 0.2. Here it is 3.1. It's really, really bad. It's 30 times worse than the normal response time. Here it is twice as bad as the normal response time. And the benefit of this is that you are able to perform small portions of the task. You are able to take probably lesser memory, lesser resources when you're doing small parts of the background task instead of doing everything together in one go. But overall utilization of the processor is better when you do things together. You centralize everything and you do everything together as one go. There is no context switching also happening. The context switching over here when you're switching to a background thread is in volume much more than it is over here. It's just one single context switch. So the question comes, which one should you go for? Things which happen in the background, right? Batch tasks, things which have no relation with latency. For example, I want to upload 50 images for safety in Google Drive. I don't care about how much time it takes me, but I want it to be done nicely. What I want is I want it to be compressed. I want the system to judiciously utilize its resources, which are always scarce. Go for a high latency, high throughput approach. Usually when you're increasing throughput, you're also increasing latency of the application. And when you're reducing latency, you're reducing throughput. You can always make it worse though. You can make it that the throughput reduced and the latency increased. So users became unhappy and your computer is also unhappy. The special case of this is thrashing. Thrashing basically means that you have a cache, or even the operating system can do some thrashing. Let's see how that can happen. You have the time slots when you need to run your application T1, and you have some background process here, and you have another time slot T2, another background process here, and so on. Whenever there is a switch from one thread to another, there's something called a context switch, which basically means that some sort of memory data structures are moved in and out of memory so that you can quickly do the task that you're supposed to do at this point. If the time slices for doing tasks is very small, then the time for context switching, this time, starts eating into your overall throughput. Okay, to the point that if you have very small tasks, like split into very small pieces, what will happen is the switching time will eat into all of your application time and even your background task time, and your throughput is going to go down. Maybe 50 seconds in every 100 seconds is just context switching. That's the reason why you can't have infinite number of threads in the processor. Let everything run concurrently. No, that's not going to happen. Every time there's a thread switch, it's going to be a context switch, and that is going to eat up some time. You don't want this volume to be very high. The idea also comes up in caching, where it's a different resource which is being pulled continuously. You have a cache, and let's say you have 2 entries only that the cache can take. First request goes to A. You pull that up in the cache. Second is B. Third is C. C kicks out A. And then you have A again. So A says the oldest entry is B, kick it out. Now you have B coming in as a request. So all you need to do is do a cyclic ABC, and these entries will keep kicking each other out. B will come in, say C is the oldest, let me come in instead of C. And you're seeing that all the reads are misses. Every read is a miss, resulting in a load to the cache. You have to load it from the database into the cache, and all you're doing is just work, useless work. The throughput is going down. The latency is increasing because you have to go and load it from the DB before you can get a response. So that's trade-off number 3. If you have any doubts, of course, leave them in the comments. And if you want to stay around for the rest of the chapter, sure, you can leave all your comments together.